Welcome back, ladies and gentlemen. Now we're moving on to 3.3 day 1, the derivative. Okay, now we're actually working out of the calc book instead of a pre-calc book, but here we go. Okay, we're going to be finding the derivative of a function using various shortcuts and rules. Okay, now we have some notational things we need to talk about because they're going to show up in the calc book that we haven't used yet in our pre-calc book, but here we go. As it says here, there's several other notations to mean derivative. Okay, we can write y with a little apostrophe right there, and we're going to read that as y prime. We can write dy over dx, which simply is read dy dx, or the derivative with respect to x, or df, and again just remember y and f of x are pretty much interchangeable, so these last three things are really the same. The only difference between these last two is you can pull the f of x in front as opposed to just leaving a single f on top. Although realistically, you could probably put an f of x up on top or just leave an f in front and it wouldn't really hurt anybody's feelings. But basically, there's a lot of different ways we can write this, so if you see one of those, just realize we're talking about a derivative. Alrighty, so as I said, there's going to be some quick rules and tricks, if you will, shortcuts. Alright, so first, quick derivatives for a constant function. Alright, if we have a constant function such as f of x equals 8, or again that 8 could be almost any number you like, basically just really quickly the derivative, which remember is just going to be the slope of that thing, and if you think about this for a second, this thing is always going to be a horizontal line, and the slope of any horizontal line is 0, so I think it makes sense that the derivative is going to be 0 as well. So there's a quick derivative. So basically, as our shortcut, our quick rule, if I've got a function which is just a number c, then its derivative is basically what I just wrote up above. It's always going to be 0. Every time if it's just a number, derivative 0, simple as that. Alright, now for polynomial functions, we have something called the power rule that allows us to take derivatives very, very quickly. This might be a pattern that you've kind of stumbled across if you've done some of the work, but let me actually just give the answers here and see if your brain can put together what's happening. Of course, I'll give you the actual rule down here, but let's just play a little bit here. There we go. So for my first polynomial here, my derivative is actually going to be 20x to the 4th plus 6x. And that's it. Alright. Let that brain work a little bit on that one. And see if we can verify your guess by saying our second one, our derivative is going to be negative 8x to the 3rd. Hopefully that matches the rule you were just thinking of. Plus 15x to the 2nd minus 12. Alright, again, hopefully some rule you were kind of tossing around in your head matched what I just did there, but for the sake of argument, here we go. For each term in the ax of n of a function, the corresponding term in the derivative is, again, notice what happened here. 5 times the 4 made the 20, and then the 5 went down to a 4. 2 hit the 3 made a 6, the second exponent became a 1, and then again here was a constant term, so it just disappeared because it became a 0. 4 times 2 became the 8 with a negative attached to it, exponent dropped down to a 3, etc. So basically each term that looks like this, you're going to take that n, the exponent, out in front times whatever coefficient was out there, and then the x is going to stay there, although he's going to lose one power as he goes. So in the case of just a first power, of course, he disappears completely. But basically that's what you got. Alright, now that we have a rule for polynomial functions, or the power rule, and we can actually apply that here in situations that aren't exactly polynomials, but if they sort of fit the basic pattern of a polynomial, meaning number x to a power, whether or not that power is actually a whole number like it's supposed to be for a polynomial, you can still use the rule. Alright, so for this guy, I've got f prime of x, again the derivative. Okay, the negative 2 comes in front, hits the 5, so it becomes a negative 10, x, and then just be careful here, I'm reducing this by 1, and if I reduce a negative number, it becomes kind of a bigger negative number, so this actually becomes x to the negative 3. Instinct for a lot of people is to turn that into a negative 1, so be careful on that. Likewise here, the negative 1 hits the 9, gives us a negative 9, but then the x to the negative 1st becomes x to the negative 2nd. Okay, again, just be careful, make sure your negative exponent becomes a bigger negative as you're subtracting 1 from it. Alright, on the flip side, I've got this expression right here, which you might think doesn't really fit the pattern so well, but the good news is, because we know good things about negative exponents and denominators versus numerators, what I can do is rewrite this original function. Okay, now notice I did not put a little apostrophe up there, so I'm not doing the derivative yet. Alright, I can bring this x to the third up on top as 6x to the negative third, and now this guy fits my power rule really, really well. So now I can go take the derivative. Notice the apostrophe shows up, and then the negative 3 hits the 6, gives us a negative 18, and then x, of course, remember, going down on that, so that's a negative 4. So there's your derivative for that guy. Or if we want to go back to the form that was originally written in, which is probably a decent idea, okay, the negative 18 stays up on top, and then the x to the fourth moves down to the denominator. I would take either one of those, but there you go. Alright, here's another function that looks very not very user-friendly right now, but the good news is this function can actually, again, turn into something that's a little bit nicer to deal with. Okay, so I'm going to turn this into f of x again. Notice I'm not doing a derivative yet, so I'm not putting a little apostrophe up there. But I want to rewrite this thing so it's a little bit nicer to deal with. Alright, so again, this could be written as, and I'm going to do this in 2 steps, sorry about this, but this could be x minus 5 to the 1/2 power, or again, in a more user-friendly form for what we're trying to do, again, no derivative yet, this guy could come up to the numerator, thereby getting rid of a denominator, x minus 5 to the negative 1/2 power. Alright, so now I'm starting to take a derivative, so my apostrophe shows up. Let me make that a little more pronounced. Alright, so again, my exponent comes out in front, so in this case it's a negative 1/2, and then my quantity, x minus 5. Okay, again, I'm subtracting 1 from negative 1/2, so then that's negative 1.5, but that's awkward, so I'm going to write it as negative 3/2. Alright, and again, that might be a little messier than what you want as a final answer, although that might be considered a good one, depending on the format you're trying to go for. So yeah, I'll circle that as one possible final answer, but I think maybe cleaning this thing up might be a little bit nicer. But whatever the case, okay, I'm going to have a 1 in the numerator because everything's coming down, although technically it should be a negative 1. I've got a 2 in the denominator, and then realistically, this guy, writing it back in a radical form gets a little messy, because then you have a radical square root, but then you have it to the 3rd power. So just for, I think, making this nicer to look at, I'm going to leave it as x minus 5 to the positive 3/2 power down there in the denominator. Again, if you wanted to, you could rewrite that as a root, but then it would be negative 1 over 2 parentheses root x minus 5 close cubed. And I don't know. I suppose any one of those 3 would be a proper correct answer, but I don't know. I don't like the root with the exponent on it. That just looks messy to me. Alright, now let's move on to some rules. Alright, we've got the product rule for derivatives, and basically what that means is if I've got some function that I can think of as the product of 2 other functions, the derivative of that original function is the first half of my product times the derivative of the second half plus the derivative of the first half times the original second half. Alright, hopefully that makes a little sense, where you can see the little apostrophe showing up for the derivative and the not apostrophe showing up for the non-derivative parts. Okay, maybe an example will help this look a little bit better. Alright, so again, here's my f of x. So now my derivative is going to be, okay, now the pattern here is I want to keep the first half of my product as is. So I'm going to keep here the 3x squared minus 7, exactly as we see them. Okay, but then I want to take to the derivative of the second half, and I don't know for clarity's sake or not, but I'm going to say the derivative with respect to x. Okay, so here's some of that derivative notation showing up of the x to the 4th plus 4. Alright, plus sign is that plus sign right there. Okay, now I want the derivative of the first half, so the derivative with respect to x of the first half, which is my 3x squared minus 7. And then I'm going to take that times the second half, which is our x to the 4th plus 4. Alright, so just be careful, this d dx here only applies to the first half of this, not the second half. But here we go. So let's clean this mess up. So my derivative is going to be my original 3x squared minus 7. Now the derivative of this guy, the 4 comes in front, and the x drops down to the 3rd power. This 4, because it's a constant, becomes a 0, so I don't need him at all. Alright, now the derivative of that first piece becomes a 6x. And again, that constant 7 turns into 0, so it's gone. And then I've got my x to the 4th plus 4. Alright, so basically I just got a little distribution to do here to clean this mess up a little bit more. So f of x equals, alright, distributing here, I'm going to get myself a 12x to the 5th, and then minus 28x to the 3rd, and then over here I've got myself a 6x to the 5th plus 24x. Alright, combining like terms, I do have a couple like terms right there and there. So as a final answer, I've got my derivative is going to be an 18x to the 5th minus 28x to the 3rd plus 24x. Alright, now that's that guy's derivative. Hopefully that didn't hurt too bad. Alrighty, maybe sometime during that whole process you thought, hey, what if we just multiplied things out first? Well, hey, let's try it and see if that messes us up. Okay, so again, f of x, okay, so I'm not taking a derivative, so no apostrophe here. So, doing my regular FOIL, if I take this times that, I'm going to get myself a 3x to the 6th. Alright, so continuing on, I'm going to get a negative 7x to the 4th. Pardon me while I do this in a good order to put in descending order. I'm going to get myself a 12x squared, and then I'm going to get myself a minus 28. Okay, now it's a nice polynomial, no like terms combined, so I can now move on to doing the derivative, and that should run very, very smoothly and quickly. I got an 18x to the 5th minus 28x to the 3rd, and then a positive 24x. That sounds fairly familiar. And a brief check. Hey, there it is. Yep, sure it is. Okay, we got the same exact thing. Okay, so basically the moral of the story there is, yes, if you can multiply things out and it creates a nicer situation, please go ahead and do that. The product rule is important though, because if you can imagine things like x times cosine of x, now that's a product, but it certainly isn't something that I can just simplify like this FOIL problem I got up here. So we do need that rule for different occasions, but we just don't have those occasions showing up quite yet. Well, it's probably not much of a shock that if we have a product rule, we might also have a quotient rule. Alright, so here it is. Okay, if I've got a function that can be thought of as a quotient of two other functions, so basically a rational function of some sort, we've got our rule here. Okay, notice that h is the denominator and g is the numerator. So I'm going to take my original denominator times the derivative of the numerator minus the original numerator times the derivative of the denominator. And I'm going to put that on top of the denominator squared. Notice it's the original denominator squared. Alright, so let's put that into action here. Alright, so my f of x equals this, and again, this is something that I can't really simplify. I mean, if I could, I would try to do it, but unfortunately, alas poor Yorick, I don't have that option. Alright, so I move right into my derivative. Alright, so again, now I want my denominator first, so the first thing I'm going to have is my x squared minus 3, and now I want to take the derivative with respect to x of the top, which is the 2x plus 5. Alright, now I got a minus sign for this, and now again, now I want the g, which is the numerator, so in this case, there's your 2x plus 5, and now I want to do the derivative of the bottom, and that's an x squared minus 3. Okay, I'm going to put that all on top of my denominator squared, so x squared minus 3 squared. Alright, so time to clean it up. So f prime of x equals, okay, the x to the third, x to the second minus 3 is still there. The derivative of this guy is a clean and simple little 2. Subtraction sign. Okay, 2x plus 5 stays right where he is, and then the derivative of this guy is a 2x. Alright, and that's all on top of this. I'll leave it to you whether or not you want to multiply that or not. Just on the off chance that something would reduce, it's best to have this thing in factored form, so I'm going to leave it this way, but if you multiplied it out to be an x to the 4th minus 6x squared plus 9, I wouldn't fault you for that. Alright, that being said, let's continue cleaning up our numerator. Alright, distributing my 2 right here gives me a 2x squared minus 6 minus, and pardon me, I'm going to distribute the negative sign as I distribute the 2 just to save us a little time here. That'll be a 4x squared, and that'll be a minus 10x. Alright, still over my little quantity squared in the denominator. And here we go. Last step, I've got a 2x squared minus 4x squared, so I've got myself a minus 2x squared, got a minus 10x, and then a minus 6, all over my x squared minus 3 quantity squared. Now admittedly you could factor a negative 2 out of the top, but it doesn't produce anything that would do any sort of reducing at all, so I won't bother. Of course, if something like that would happen and would create a reducible situation, I would definitely want you to do it. But there's your quotient rule in action. Alright, now here's kind of a messy situation with the quotient rule where I have a nasty product sort of thing on top and, well, something nice on the bottom. But so basically this is one of those situations where I could use my quotient rule as is, but as I'm doing the one part, I'm going to have to do the derivative of the top. And in doing the derivative of the top, because this is a product, I would then have to do the quotient, or sorry, the product rule in amongst doing the quotient rule, and I think that would just be a big hairy mess. So what I would do first, before I did anything else, is FOIL this guy out. So this would create an x to the fourth plus 9x squared plus 20 all over the x to the third. Okay, and that's just a much nicer function to deal with. Alright, so now moving into things, and instead of an f of x here, I've got a y, so don't freak out, it's just going to be y prime instead of f prime of x. Alright, so again, denominator first, x to the third, and then I'm going to take the derivative of the numerator, which again I'm going to go with my simplified version of the numerator, just because it's easier to work with. X to the fourth plus 9x squared plus 20. Okay, and then again minus, and you just kind of change the order of things, keep the original numerator, x to the fourth plus 9x squared plus 20. And then now I'm going to take the derivative with respect to x of my denominator, which is x to the third, and that's all over my x to the third, my original denominator, squared. Alright, so again, cleanup time. Alright, x to the third is happy as a clam, and then I've got a 4x to the third, again just applying my power rule here, plus 18x, drop down to the first power, the 20 goes away, so that closes up, and then minus, this becomes a, I'm going to do this, cheat and do this first so it looks a little bit nicer later, 3x squared, and then again this guy's going to stay right where he is, x to the fourth plus 9x squared plus 20. Alright, okay, now here in the denominator I will put this into x to the sixth because quite honestly there's no factoring to do or anything like that, so x to the sixth is just easier to work with than x to the third to the second. Alright, a little more cleanup is in order. I'm going to distribute my x to the third and get myself a 4x to the sixth plus 18x to the fourth. Distributing my negative 3x squared gets me a negative 3x to the sixth minus 27x to the fourth, and then a minus 60x squared. Okay, now I do have some like terms there on top of my x to the sixth, so I'm going to put those together. I've got an x to the sixth here and an x to the sixth there, although they conveniently cancel down to 1x to the sixth, so there's an x to the sixth. Okay, I've got x to the fourths, I got an 18 and a negative 27, so a negative 9x to the fourth, and then finally I've got a 60x to the second, negative version. Alright, on top of my x to the sixth. Okay, now for space concerns I'm going to move this guy horizontally, but if you notice here, everybody's got some x's in them. In fact, everybody's got at least 2. So what I can reduce this thing by is a x squared. And so as a final answer right now, I'm going to have x to the fourth minus 9x squared minus 60. That's all sitting on top of an x to the fourth. Okay, so there's our derivative of that guy. Yes, it is a little bit messy, but that's the hand we've been dealt. So there it is. Alrighty, and there's our assignment. Okay, for 1 through 10, it does ask you to find both the first and second derivatives. Since we haven't talked about what a second derivative yet, just find the first derivative, which again is dy dx, just means first derivative. There's your even answers. And as always, if there's anything that you weren't sure about, please ask me in class. I'll see you then.